Substances in our universe are made from lots of tiny particles, and the way these particles interact in substances is called bonding. If we talk only about solids, then there are generally four types of bonding: ionic bonding, metallic bonding, covalent bonding, and molecular bonding. In this video, we will discuss the tool we use to describe molecular bonding, the Lennard-Jones potential. As its name suggests, this type of bonding is the interaction between molecules. The origin of this bonding is the attraction and repulsion between molecules, often described by the Lennard-Jones potential. We denoted the potential as V, and it is a function of the distance r between two particles. Its mathematical expression looks like this.
If we plot the potential against distance, the graph takes the shape of a well, which is often called a potential well. The other two quantities in the equation, epsilon and sigma, are constants that depend on the type of particles we described. Now let's take a closer look at the function. Remember, we said that the potential describes the result of the attraction and repulsion between molecules, so these two terms correspond to the two directions of force. Imagine two particles in space. We'll want them to repel each other as they come very close, because otherwise all particles will simply stick together when the distance between them is small, and the substances will thus collapse. The physical origin of this repulsion is the Pauli exclusion principle. Now, if we separate two particles at a relatively large distance, we would expect them to attract each other, and the physical reason of it is that at this distance, the van der Waals force becomes significant. Therefore, for small r, we want large positive V to repel particles, and for large r, we want small negative V to attract. Then we know the term 1 over r to the power of 12 is responsible for repulsion, as is in fact the case much faster than the power of 6 at large r. Similarly, for small r, the term 1 over r to the power of 12 will dominate, giving large positive V, and together they give the shape of our graph here.
A good way to think of it is taking the potential as a real valley and considering the particle as a ball. If the ball is at a very large distance, it will roll slowly towards the bottom of the valley, and if we place a ball at a very small distance, it will roll down to the bottom very quickly. But in either case, it will eventually stop at the bottom. This position is known as the equilibrium position, where the repulsive and attractive forces are equal and the potential is at its lowest. We can find the coordinates of the equilibrium position by working out where the gradient of the line is equal to 0. To do this, we need to differentiate the function and find out where this is equal to 0. The function differentiates to give this. We can then rearrange to solve for r, and we eventually come out with 2 to the 1 over 6 times sigma, and we'll call this r0. We can also think of this as the point where the force is equal to 0, since the force is also equal to dv by dx. And now that we know the equilibrium position, we can substitute this back into our original equation. This can then be simplified, giving us v of r0 equal to minus epsilon. And this is the depth of the well. Here we can see how the values we have just calculated are represented on the graph. There is also a third value on here which represents where the line crosses the horizontal axis. This is found by setting the equation equal to 0 and solving for r. We won't go through the steps for this, as it is just a case of simple rearrangement. This comes out with a solution that r is equal to sigma, as we can see on the graph.
As we know that this potential describes the interaction between particles in certain types of solids, then some properties of the solids may be the result of the form of the function. An example would be the thermal expansion of solids. In high school, the explanation usually given to this is that we know temperature is a measure of average kinetic energy of particles. So when temperature increases, particles are given more energy to vibrate in all directions at its equilibrium position, thus taking up more space, and the overall behavior is thermal expansion. However, this explanation is incomplete, because if a particle vibrates equally in all directions, then the average distance of a particle moving towards and away from another particle should be the same. So the particle's average positions stay the same. Then there should be no change in the volume of solid. To resolve this contradiction, the new explanation must state that on average, the distance of particles moving away is larger than that of moving towards each other, meaning that the net effect is the average distance between the particles increases. To figure it out, we'll look back at the graph again. We can see that the bottom of the well is not symmetrical. It is steeper at smaller values of r and flatter at larger values of r. And if we use the valley analogy again, we can imagine that if the ball vibrates around the lowest point, it would spend more time to the right of the lowest point than to the left of the lowest point. This means that the ball is spending more time on the side with greater r values, and therefore the average net change in distance increases, so overall this results in an expansion. From this, we can see that the reason why the explanation from before does not work is that it assumes the potential well to be symmetric.
Thank you for watching the video.